Hello, and welcome to this next installment on our series of shellcode obfuscation techniques. So, in this series, or this particular installment, we're going to take a look at some different encryption techniques. We're going to look at some pretty basic to some more advanced encryption and see how those work out. So, let's go over to our VM. Okay, so what I have here is a Python script. Actually, I've got two of them that will be used in this demonstration. So first, I have this one called zor.py, and it contains some shellcode. These are the standard shellcode we're used to seeing here: 0xFC 48, 83, E4, and so on. And all it's going to do is print out the result of the XOR or XOR operation. So this is a simple logical operation here. And if you take a byte and you XOR it with itself, you get zero. If you take a byte and XOR it with some key, and then take that encrypted value and XOR it with the key, you'll recover the plain text. So in this script, we're just going to generate a random key. We're going to print that key out, and we're going to encrypt our shellcode. So let's take a look at that. So here you can see it says our key is 105, and it prints out some results. It's printing these values out as integers, which is something we could use. We could just as easily do this in hex, but it happens to be printing out in integers. So let's take a look at our shellcode program, or our example program, I should say. So in this example, we've got our shellcode, we've got some bytes here. So these are just a bunch of integers. And then we have a XOR key. So in this case, the XOR key was 51. And to recover the plain text, or in this case, our shellcode, all we need to do is loop through that array of shellcode and XOR the value with the key. So we're going to do this in place. We're not actually creating a new shellcode array. We're just going to do it in place, and let's test it out. So we can see when it runs 0xFC, 48, 83, and so on and so forth, and ends in FFD5. And if we were to test that, we'll see Defender does not detect it. Let's see what happens with virus total. So as it's processing, we can see we have one detection already, and then two, four. So definitely things are detecting this. And it looks like we're at seven right now. And if you've ever used virus total before, or if you haven't used it and you start using it, you'll find that sometimes you get one score, you run the same thing a second time, you get a different score. Uh, it's not an exact science with the way these engines are working all the time. So we can see that we scored an 8. I think in the previous example, we got maybe 7. So Caesar Cipher might score slightly better than XOR, a standard XOR with a single byte key. Let's go ahead and take a look at maybe a better way of doing that. So another way that we could do it is do XOR with a multi-byte key. So looking at this Python code, I've got a key. My key is going to default to XOR key, and then we're going to read in a file from the command line using the dash I or dash dash input argument, and we're going to get the results. So it calls do binary. If we look at do binary, we see that we're going to read our raw shellcode. That's what's happening here. And then we've got our key. We're converting our key into a bytes object. And then we're going to encrypt our shellcode by calling repeated key XOR, repeated key XOR. And if we look at our repeated key XOR routine, we're going to give it our input text, which is going to be our shellcode. We're going to give it our key. We'll figure out how long that key is. And then we're going to create a new list called encoded. And what we're going to do is create a loop for I in a range of 0 to the length of the input text, so the length of our shellcode. We're going to populate the encoded or list, rather, not array, with the current indexed value at input text, XORed with the key, but we're not just giving it the whole key. What we're going to be doing is iterating through the key bytes. So if the key is XOR key, the first iteration will be XORing that with an X, the second with a O, the next with an R, and so on and so forth. Of course, it's doing that with a byte object, not with the text itself, because we converted that to a bytes object down here. So let's take a look at that. Uh, and it's going to put the output in a file. So here is our output. We've got our output with a variety of values here. So we've already done this. Let's go over to the Windows VM and take a look at the code. So here we've got a key, which is XOR key. So we can see that's the key that we defined earlier. These are the shellcode bytes, 0x4a, 0x07, 0xD1, and so forth. So these are the shellcode bytes that have been uh, run through that XOR multi-byte key process. We have a function called XOR where we pass it our shellcode, the size of the shellcode, the key, and the size of the XOR key. And because it is a void type, it's actually just going to do this in place rather than returning a new object with the decoded shellcode. And if you see this right here, this is because Defender does detect this XOR with a multi-byte key routine. It's very good at detecting that, even with compiler optimization disabled. So in this instance, rather than doing a printf, what I'm going to do is I'm going to open up the null device, and then I'm going to write to the null device at some point here. And that will help, uh, that'll help, you know, throw off that detection. And in this case, it might not even be necessary. Just sometimes just opening up the out file or opening up the null device and closing it can be enough to do the signature. But that's it. Then we're just going to print out the results. So let's take a look and see if it works first. Um, so it runs and we see the output FC 4883 E4, just like we're expecting. If we go to the end of our output, we can see it ends with, well, something a little bit different. So this might actually be some different shellcode that I gave it uh, rather than the standard shellcode that we had. So this is a slightly different version of the shellcode, and that is fine. Let's check to see. Is with the 9E. Nope. So had a slightly different result here. Just so it matches up with our program, let's go ahead and replace that. And then we'll compile the program. Aha, we have a problem. There we go. There we go. So we were using a different shellcode example than some of the ones that we will look in this series. So you can see here starts out with FC 48 83 E4 and it ends with A256 FFD5. That's the same example that we're looking at elsewhere in the series. So let's test it out. No threat found. That's great. So now let's go ahead and upload that to VirusTotal and see how it fares. You see already we've got some detections. And there you have it. This particular time of testing, Zor with a multi-byte key was detected by 12 of 72 security vendors. And we can see those vendors here that got that detection. So there are some vendors that are detecting Zor with a multi-byte key. So this may not be our best option for doing evasion. We have one other option and to look at here today, and that is going to be AES encryption. So we'll go here. So this is something pretty simple. We're going to import some libraries. We're going to generate a random key. We're going to generate a null IV that's 16 bytes long. We're going to initialize a new cipher. And then we're going to encrypt our plain text. In this case, our plain text is our shellcode file. And then we're going to print out uh, the encrypted shellcode. So let's take a look at that. So now we have an AES key that it has generated, and we have our payload array. So we've already generated this over on our Windows system. Let's take a look at that. So here we have some encrypted shellcode. So obviously this isn't the normal bytes 0xFC, uh, 4883, E4, so on and so forth. This has been encrypted. And we've got an AES key and we've got our AES encrypted shellcode. Now we're going to call our AES decrypt routine, which is pretty straightforward. There's not much to look at there. So we'll test it out. We'll see how it works. Hmm. I wonder what we have here. There we go. So this again must be using some different shellcode than the other shellcode that I generated earlier because we can see it starts out with FC 4883 E4, F0, ends with a bunch of zero A's. Oh, no, it doesn't. So we've got, here we go. It's A2, 56, FF, D5. The rest of that is padding. So that's what happened there is that ended up being padding. Being padding with a zero A probably isn't the best, so we should maybe fix that, but it works for our demonstrations purposes here. We printed out the values. We have the shellcode that we recovered. The reason that that is longer than the original shellcode is because of padding, because of how AES works. So let's take a look and see if Defender detects that. Defender does not detect it, which is great. So let's go ahead and check it out with virus total. We can already see that there are some detections. So in this case, it's highly unlikely that it's detecting the shellcode itself. What it is detecting is the technique. And what's probably happening here, it's tough to say because we don't have insight into what's going on, but we see that there's at least 11 engines that detected this. If we look at our program, we see that we don't have really anything in here. We have some shellcode. We have a routine to decrypt that shellcode. We've got a key for the encrypted shellcode, and then we print out the results. So there's not a lot going on here. There's a lot of entropy, there's a lot of random data, and not a lot of usable code. So our ratio of usable code to high entropy bytes is really off, and that could be a signal that we're trying to hide something. And that's why 12 out of 71 of the engines found this as something that's bad. So now that we've taken a look at this, we can see that AES encryption works great. We know it's secure. It's a great routine. However, the entropy problem is something that we might have to solve. So our program might need more code to throw off the engines to have more lines of code to the amount of encryption or encrypted data that's in there. We could try padding the program with non-random data, things like arrays of words and things like that. A lot of different ways we can solve this problem. But now we've looked at a few different encryption routines that we can use to obfuscate our shellcode. Stay tuned for the rest of this series where we're going to look at a bunch of different techniques for obfuscating shellcode. I think you'll enjoy it. Thanks.